Alright, this is a video showing a frequency modulation using the NE555 timer. So in the circuit, I have this NE555 timers put in astable oscillation mode, putting out a PWM square wave that is the carrier frequency to the loudspeaker. And then I'm modulating this carrier wave using this NE555 timer here, the second circuit. And this circuit will output a square wave that is of a much lower frequency with a period of more than 1 second. It's adjustable. And it's getting fed into pin 5 of the carrier frequency to modulate it. And the result is that we have an audible frequency coming out of this modulation, coming out of this carrier wave. It's around 1 kilohertz, so that's within the audible range for humans. And that frequency shifts around the 1 kilohertz mark because of this modulating circuit. So I'll just demonstrate this, and I'm turning the power on. This is supplying 5 volts, and this is a loudspeaker. And I'm going to put these 2 pins, which is the output, to this. And you can see that it sounds. And I'm going to first change a few things. So, alright. Alright. So as you can see, there's basically 2 tones of the siren. And I'm going to change a few of these potentiometers to adjust. So first, I can change this potentiometer to change the time delay of the 2 pitches. So make it faster, make it slower. This is faster, this is slower. So this is an ambulance sound. Next is I can change the volume by changing this potentiometer. And adjust it here. This one, I can change how close the pitch or the frequency of the 2 different sounds are. So you can see that's further apart now. And it's closer now. So over here, that's good. And lastly, I can change the carrier wave frequency as well, which will change the average frequency of the whole output. And a lot higher. Yep, and that's the demo for the circuit. Next, I'm going to talk about how the circuit actually works. So, first thing to note is how does this loudspeaker actually work? In the loudspeaker, I'll just peel it off. So this is what it looks like. There's a coil of copper wire in here that, when you put a current through, generates a magnetic field. And through Maxwell's laws, when you have a magnetic field that's fluctuating because there's an AC signal, it's going to push a current carrying object. It's going to induce force on a current carrying object. And that's what it does. So essentially, there's a magnetic field generated through a coil, and then there's going to be something in the middle that moves back and forth as the current changes direction. And as it moves back and forth, it shakes this membrane. So this membrane here. And yeah, it's also a magnet, as you can see. So yeah, basically a magnetic field generated by the wires interacts with this magnet, and then it shakes the membrane. And the faster it shakes it, the more it compresses the air in front. And when the frequency is at a certain range, that compression in the air is audible by humans. So that's what I'm doing, is basically passing in a voltage frequency centered around 0, a AC frequency that has a frequency audible by humans. And the way that it's doing two sounds, as you saw, because this is a siren, right? It's got two different sounds, is that it's got one frequency followed by another after some time. And the way that this is getting generated is through this circuit. So here I have one NE555 timer configured in the carrier frequency output. So it outputs a square wave that has about 1 kilohertz in frequency. And the NE555 timer in astable mode to generate a PWM square wave looks like this. I'm not gonna go over this in too much detail. Watch my previous video where explained this more. Yeah, but in a nutshell, there's a trigger and threshold pin that when you pull the voltage high or low on them, the output changes in high or low. So what we do is we feed a voltage in here from VCC, and it toggles between VCC and ground because there's a drain through the discharge that is set by an internal transistor that turns on and off based on what the output is. And also there's a capacitor here that delays the response. And for the output to pull high, the pin 2, so the voltage coming into this junction, needs to be, because threshold and trigger are tied to the same node, for the output to pull high, the voltage needs to drop below 1/3 of VCC because there's a 5K, 5K, 5K voltage divider inside of there. Let me just show that. So here, there's a 5K, 5K, 5K. This is the NE555 timer's internals. And to pull high, it needs to be higher than this voltage. So it needs to be higher than 2/3 of VCC. So that's how the frequency modulating generator works. The carrier wave is generated by this, and then the frequency modulating wave is generated by another 555 timer set up in a PWM configuration. That's basically exactly the same as this one, except the output is going to pin 5 of the frequency generating configuration. And why is this a frequency modulation? So I actually didn't understand this when I first looked at the theory. Why is it that when I feed in a voltage into pin 5 that it changes the frequency output of the PWM? And the reason is because the frequency of the output is determined by the time it takes to charge the capacitor from the difference between these two op-amps. So normally without a frequency modulating voltage, the time is to charge up from 1/3 VCC to 2/3 VCC, these two, and so that's the on time, and the off time is the time it takes to discharge from 2/3 VCC to 1/3 VCC. So that gives the off time of the frequency modulation, of the carrier wave, sorry. But when I set this control voltage, it overrides this comparison voltage. So now instead of charging from 1/3 to 2/3 VCC, it's charging from 1/3 to another voltage. So either above or below 2/3 VCC. And that difference is going to change the time it takes to charge the capacitor up. And also change the time it takes to discharge from that voltage back to 1/3 VCC. So that's why this is a frequency modulation. By passing in a voltage here, we can override whatever voltage or shift whatever voltage is on the original node, which is 2/3 VCC, and then change the time it takes to charge and discharge this capacitor C1. So yeah, when I built the circuit, I ran into a bunch of problems, and I wanted to just quickly go over those things and how I fixed them. So first of all, my original configuration here, I had it set up such that there's an R1 and then R2 is bypassed by a diode. So therefore, the charging only goes through resistor 1, and then it bypasses through the diode. And this charging only goes through resistor 2, and it's blocked by this diode, right? So therefore, the duty cycle can be modified by changing the ratio of R1 and R2, but the frequency is still the same, because by using a voltage divider using a potentiometer, R1 plus R2 is still going to be equal. So when you switch the position of the potentiometer, the two different resistances are always still going to sum up to the same total value. So I had a setup where you can twist the knob and it changes the duty cycle, but it does not change the frequency. However, I want the opposite effect, because when you create a carrier frequency to power a loudspeaker, you want the duty cycle to always be at 50%. The reason is because if you start varying the duty cycle to less or more than 50%, then the odd harmonics consisting of that square wave is going to be larger. So the odd harmonics are the smallest when the duty cycle is 50%, which makes the square wave closest to its fundamental sine wave frequency. And what happens if you change the duty cycle is the sound just starts sounding more and more chopped and weird, because it has all those higher harmonics added into it. So I wanted to change the setup such that I can change the potentiometer and change the frequency but not change the duty cycle. So the way that I was thinking about this is, well, there's a couple ways that I tried. So first of all, in the original setup, we have a resistor going to VCC to discharge, and then two resistors over here that both have opposite direction diodes. And the duty cycle, for it to be 50%, you cannot have a single potentiometer change the frequency. It's just not doable because of the math. So then I thought, okay, what if I had something like this, where there's only a single resistor and the path it takes to charge and discharge both go through R1. So for example, to charge, it goes from VCC down to the capacitor, right? Goes through R1. And then to discharge, it goes from capacitor to pin 7, also through R1. So therefore, it doesn't matter what R1 is, the duty cycle is always going to be 50%. And by changing R1, therefore, I can change the period or the frequency while having it still be a 50% square wave. And this would work, except that by not having a resistor up top, VCC connects now directly to the pin 7, and then it's going to short the supply voltage when the duty cycle is on. So that's not going to work, because now the current is going to burn through the internal resistor, burn through the internal transistor of the 555 timer. So then I thought, okay, well, we can't just put a resistor here, because then it becomes basically the original problem. We can never achieve a 50% duty cycle by changing the frequency. But what if we did something like this, where we had two resistors here that are of equal value, and so therefore, let's say R1 and R2 are both 1K. So therefore, charging is going to go through VCC through here. It's going to go 1K plus R2. And discharging is going to go through here like this, where it goes 1K on R3 plus R2 again. So therefore, the resistance path is now the same, right, for charge and discharge. And there's also a resistor between VCC and the discharge pin. So now there's no short going on. And I thought this was, this might work, but actually this does not work. The reason is because by setting these two resistors, you actually put a voltage divider here. And when the VCC is discharging, this actually sets the voltage of this middle pin. It skews the voltage. So it no longer will have a 50% duty cycle because of that. In fact, it will just not even generate the square wave, because this voltage sometimes will just not reach the threshold required. So then I thought about, okay, what if I did this? This sounds like a very smart plan. What if I connected the output directly to a transistor that controlled whether or not voltage flowed through VCC? Because what should happen, right, is that when the output is high, we want the current to flow through VCC because it needs to go and charge this capacitor. And at this point, when the output is high, the internal transistor is turned off, so therefore no current will flow through here anyway, so it doesn't matter if it shorts it, because there's no current that can possibly flow through the internal transistor in pin 7. And then when the output is low, this transistor gets turned off, and this capacitor drains through pin 7 without being interfered by VCC. So this sounded like a really good plan, and I built this and it did not work. It did not even generate the square wave. The reason for that is because the output that you get here is not actually at VCC. The output of the LM555 timer is always going to be below the VCC voltage. In fact, for what I measured, it was 3.8 volts with a 5 volt VCC output, with a 5 volt VCC input. And so the output, what happened is, because it's passing in 3.8 volts, it's going to push this pin down to 3.8 minus 7 volts, which means that this pin, when the voltage flows through it, is actually at I think it was 3.2 or 3.1 volts. And that means that it never passes the 2/3 VCC threshold required for the current to turn off. So for the output to pull low. So it didn't work. So what I ended up doing was I gave up on trying to find a perfect solution, and I just ended up adding a resistor here with a very low resistance compared to the common resistor. So therefore, the charging current is going to have to go through 200 ohms plus, let's say, 5K. And the discharging current is going to go through 5K. So the two resistances are very similar, although it's not going to be a perfect square wave anymore. It's close to a 50% ratio. Another problem with this is because this resistor is so small, it's going to generate a high current through pin 7 on discharge, and that's just something that I'm going to have to live with. I'm sure there's a way to do this perfectly to achieve a 50% duty cycle on a varying frequency perfectly, but I didn't bother going any further because this one didn't work. So I just ended up sort of using a good enough solution there. So that's what basically this potentiometer is. It changes the frequency of the modulating square wave. The next thing that I did, give me a sec, let me put this back into place. The next thing that I did was how do I turn the output into a volume adjustable voltage. And the thing that I was doing was basically the output is a square wave that's centered at half of the output voltage, which is around 2.2 volts. Oh, sorry, it's 3.8 output, so that's about less than 2 volts basically. But it's going to go from 0 to about 3.8 volts. And in order to drive the speaker, I needed to be centered at 0 volts, because otherwise having a DC voltage through the wire is going to be producing a lot of heat. You actually need a basically frequency centered at 0 in order to, cleanly generate the audible sound. So what I did was I just put a capacitor in series with the loudspeaker, and the capacitor acts as a high-pass filter, and I picked the value of the capacitor to be really large because the resistance of the loudspeaker is actually quite low. It's only 8 ohms. And basically by using a voltage divider with the potentiometer here, I can set the voltage across the loudspeaker, and when you have a higher voltage, it drives a higher current, so therefore it drives a higher volume. And a lower voltage, vice versa, will have a lower volume. So basically it goes through a series capacitor for decoupling the signal, so basically having it centered at 0, and then a voltage divider to adjust the volume before connecting to the loudspeaker. One thing that when I was designing the circuit I was afraid of was like, well, the modulating frequency is very low, right? It's, less than 1 hertz sometimes. Is this filter going to mess with that? Because that's very close to a DC voltage. And then I realized that actually the output voltage is not close to 1 hertz. It's actually close to the modulating frequency, because the frequency is getting modulated. Like, it's not actually, it's not like it's 1 hertz plus, it's not like a 1 hertz wave plus a 1 kHz wave. It's a, plus or minus, like, let's say 500 to 1.5 kHz wave coming through here. So this capacitor alone is good enough to do that. Cool. So that's that. The next thing is I wanted to figure out is like, how do I vary the 2 frequencies that are getting generated by this frequency modulating circuit? And because it's a frequency modulation passed into pin 5, it doesn't matter how you change the duty cycle of this, the frequency of the frequency modulating output. The high and low are always going to be pulled from 3.8 volts to 0 volts, regardless of the frequency. So in order to change the 2 pitches, I have to actually change the 3.8 volts and 0 volts being passed into pin 5. And to do that, I put a potentiometer here that basically acts as another voltage divider for that voltage. So I want to just quickly go over this principle here. So inside of the 555 timer, there is a 5K voltage divider, and I want to see what happens at this junction when I pass in a voltage with an input impedance. And this is simulated by basically this circuit. Basically there's a 5K ohm tied to a 5K voltage supply, and then there's a 0 volt here that passes through 10K to this node. And then the frequency modulating voltage has to pass through some sort of a resistance, and it goes from 0 to 3.8 volts into here. And I want the output voltage to not swing lower than 1.8 volts or higher than 4.8 volts. The reason is because if this node swings below 1.8 volts, what's going to happen is there will no longer be a point. It's actually supposed to be 1.66, but I put 1.8 for safety. There's no longer going to be a point where the set pin turns on again, because the set pin has to be higher than 1.66 volts. And likewise, if it's higher than 4.8 volts, if this node is higher than 4.8 volts, there's going to be no point where the reset pin turns on, because the reset pin can only pull up to 5 volts. So basically, by having these conditions and running KVL on this point, so all the currents flowing in and out of this node has to be summed up to 0. I come out with the resistance has to be bigger or equal to 3.9 k ohms. So therefore, if I use a 50k potentiometer, I can basically vary the frequency as long as it's above 4k set on the potentiometer. It's going to vary the frequency to a pretty decent level. So that's basically how I did it. If you want to calculate what the frequency output actually is, you can just plug in the resistance into here, and it's going to be from 0 to 3.8 volts through this resistance. Run the KVL, and you can get the frequency of this output, and then you can use the capacitor charging time to figure out the on and off cycle. One interesting thing that I noticed was when you change the voltage control voltage through frequency modulation, the duty cycle of the carrier wave output is no longer going to be at 50%. That's very strange to me at first, because I'm like, isn't it charging up and down the same amount of voltage? And it is, because it's charging up from 1/3 VCC to whatever this voltage is here, and then it's discharging the same from this whatever this voltage here down to 1/3 VCC. But the reason why the duty cycle actually changes and the time of charging up and down changes is because when it's charging up through this 5-volt voltage, and when it's discharging, it's no longer discharging through a 5-volt. It's discharging from whatever this voltage is. So therefore, the only time when the duty cycle is 50% is when the difference between this voltage and the 5-volt is exactly the same as the difference between the 1/3 VCC and 0 volts. And so therefore, the duty cycle is going to be changed if you change this 2/3 VCC voltage through the frequency modulation. And so that's what this resistor is for here. It changes the basically the voltage divider going into the 2/3 VCC, and then you can modify the two frequencies by changing this voltage divider. Lastly, this potentiometer is the time it takes for those two pitches to play. And that's essentially just changing the frequency of the modulating wave. And I've set this potentiometer, it's the exact same setup as the frequency modulating potentiometer. It's just that it has a much larger capacitor and resistance, because I want it to be in the seconds range. If it's too quickly, the is going to be like too quick in order to show up properly. So yeah, that's it for the video.